This is the second video on buffers. This is an alternative way of calculating the pH of a buffer. You're going to like this. There's a shortcut. You don't have to do a big ice table. You can use something called the Henderson-Hasselbalch equation. These are, well, they were given in the packet. This year, only the acidic version of the Henderson-Hasselbalch equation is given in the AP packet. I have no clue why the basic version is not. I mean, you can deal without it, but it makes me think that they'll probably just give you an example of an acidic buffer. Or maybe if it was a basic buffer, it would be more of a qualitative problem. We need the pKa, which is actually just opposite log of the Ka value. Then we're going to add the log of two concentrations, a ratio of two concentrations. On the bottom, this would be the weak acid over the concentration of the conjugate base. Or if I was doing the basic version, I would be calculating a pOH. I would need opposite log of the Kb plus, and again, here's this ratio. On the bottom, it would be the base, and on the top, it would be the concentration of the conjugate acid. So for the most part, these are plug and chug. We can calculate the pH of this lactic acid buffer. It is a buffer solution. We've got a weak acid, lactic acid, and we've got its conjugate base. It's coming from a solution of sodium lactate, but the sodium is a spectator, so we're going to have the negative lactate ion, which is the conjugate base of the weak acid. You can write the equation either way. You can write the original weak acid, H5O3. You can put the water in if you like to. We're going to lose a hydrogen, so that will form the lactate ion, which is negative, and then hydronium, H3O plus. Or you could just start with this original lactic acid neutral particle, and you could dissociate that right away into the lactate ion and hydrogen. Either way, numerically, your calculations are going to end up the same. So I kind of think about what I have. The original solution is 0.75 molar lactic acid. I'm not really going to care about the water in the end. I get it. Water's a pure liquid, but I kind of like to show it. And then the lactate ion is 0.25 molar. Initially, we have no hydronium or hydrogen. We know that we will at equilibrium. But instead of having to solve this thing for X and set up a big ice table, you can plug and chug using the Henderson-Hasselbalch equation. pH, this is an acidic buffer. So I'm going to go opposite log of the Ka value, 1.4 times 10 to the negative fourth. Plus the log of the conjugate base over the weak acid. So it's going to be the 0.25 molar lactate ion over the 0.75 molar lactic acid. There, you plug this in your calculator. If I wanted to kind of simplify it, this ends up being about 3.85-ish. This other one ends up being about like negative 0.477. And then I just plug this in my calculator. So I should get a pH of approximately 3.37. How do you like that, huh? It's just a little quicker. And eventually we're going to get to a point where we might want to do this quicker than setting up multiple ice tables. So you can use this Henderson-Hasselbalch. It's a nice little shortcut, and it is just plug and chug. The basic version would be really similar. I don't know why they don't give you the basic equation in the packet anymore. Here's what we can do with this. Here's a good example of a basic buffer. We could calculate the pH of a basic buffer as well. I like to write the equation. I'm going to have, a weak base and its conjugate acid. We've got the ammonia, which is the weak base. The conjugate acid being the ammonium ion. Chlorine is a spectator. All right, so let's set up this equation. We've got the weak base the ammonia. There's always water in the solution, and I always put water in for a weak base equation. We're going to form the ammonium ion, NH4 plus, and hydroxide. There, that's a hydrogen. All right, so what do we got? 0.25 molar ammonia. And then we've got 0.4 molar ammonium ions. We don't care about the water, and initially the hydroxide is 0. If you insist, you can set up an ice table, and it would be totally fine. You can solve for hydroxide, take the opposite log, you're good to go. Or you can use Henderson-Hasselbalch shortcut. For a basic buffer, which another sign that this is a basic buffer is they give me a Kb value. I'm going to end up calculating the pOH is opposite log of the Kb, 1.8 times 10 to the negative fifth, plus a log. It's always the conjugate over the neutral particle. So this will be the 0.4 molar conjugate acid over the 0.25 molar weak base. You plug it all in. If I simplify this a little bit, I'm at like 4.74-ish. And here I get about like 0.204-ish. I plug it in my calculator to get the pOH as about 4.94. And then I can just subtract that from 14 to get the pH. The pH should be about like 9.06. That makes sense. It's a basic buffer. To get the pH, all I did was subtract that from 14. So you can use this for acidic buffers and basic buffers. It's real similar for the base. It's just that you're going to calculate the pOH. Maybe that's why they didn't put it in the packet this year. It's opposite log of the Kb plus log of the conjugate over the neutral particle. I don't know if you just heard that. There was like an announcement on the loudspeaker about going to a book study in the LMC. If you heard that, I'm sure it's exciting. I'm not going. I'm going to stay here and talk about buffers some more. Here's some more good things we can do with the buffer solution. Using this Henderson-Hasselbalch shortcut. So what if we want to play around with the buffer and we want to add something to the buffer solution? We've got the same solution from above, so we're going to use that basic buffer, the ammonium buffer solution. What else are we going to do to it? We want to know the new pH after we add 0.1 moles of gaseous HCl to a liter of the original buffered solution. So again, sometimes I kind of like to think about what all is in this solution. The original buffer has the NH3, the ammonia. It had the ammonium chloride, which will be ammonium ions and chlorine ions. There's always water in any solution. And now we're going to add some HCl, strong acid. So there'll be some hydrogen, that's a hydrogen ion. And there'll be some chlorine ions. We're asking ourselves, what's going to affect the pH? I added some hydrogen and some chlorine. And hopefully our answer is the hydrogen. This chlorine in both cases is a spectator. Chlorine has no effect on the overall pH, the hydrogen concentration. It's that hydrogen. We're adding extra hydrogen. So when I set up my equation, sometimes that's like the hardest part for people. They don't know where to start. We're going to need to put hydrogen on the reactant side. We're adding hydrogen. The other particle that goes on the reactant side is the particle in the buffer that can react with the hydrogen. So in this case, it'll be the base. The ammonia can react with the hydrogen, and we can form this guy, NH4+. We can form that ammonium ion. So again, I'm adding extra strong acid, but I'm going to exchange that for the formation of a little bit of weak acid. The ammonium ion is weakly acidic. That should have less of an effect on the pH than having a whole bunch of extra hydrogen ions free floating in the solution. So we write down what we know. I'll start this as an ice table. The original buffered solution was 0.25 molar ammonia and 0.4 molar ammonium ions. And now we're adding hydrogen. We're adding 0.1 moles of hydrogen per liter of solution. So again, this is kind of what I call the BS, or the buffer stoichiometry, the BS. So I guess before I can calculate the pH of this solution, I do have to do a little bit of an ice table. I have to figure out how these concentrations are going to change when I try to remove that extra hydrogen. Essentially, this is a limiting reactant situation. We want to react all this extra hydrogen so that at equilibrium it goes down to 0. So everybody else changes accordingly. The ammonia will go down by 0.1. So at equilibrium, it'll be 0.15 molar. The ammonium ion will go up by 0.1. So at equilibrium, we'll be at 0.5 molar. Here's where the shortcut comes into play. Now, before, the way that we did it in the last video, you had to do another ice table and figure out, like, how much is that ammonium ion going to dissociate? Or you can Henderson-Hasselbalch. We're going to do a basic buffer. The pOH is opposite log of the Kb, which is 1.8 times 10 to the negative 5th. Plus the log of the conjugate over the neutral particle. That's the 0.5 molar ammonium over the 0.15 molar ammonia. That's the change. So by adding that extra hydrogen, I do change the concentrations of the other ions just slightly. If I wanted to kind of simplify this a little bit, I would have about 4.74 again. And then this ends up being about like 0.523. So my pOH is about 5.26. If I subtract that from 14, I get a pH of 8.74. That's not bad. The original pH that we calculated for this buffer was like 9.06. We just added strong hydrogen, strongly acidic solution. The pH changed ever so slightly. Did it go down? Oh, sure. It went down a little bit. But not as much as if I would have added it to water. If I added 0.1 moles of HCl to a liter of water, I would have had a huge change. That's kind of the beauty of a buffer. We resist a major change. In exchange for getting rid of the extra strong acid hydrogen, I made a little bit extra of this weakly acidic ammonium ion, which has less of an effect on the pH.